Welcome to the actor part of the reactive programming course. This week we will learn about the actor model. That means what actors are, how they interact, what they can do, and in general how you can structure your computations using actors. Last week we saw what reactive streams can do for us, how data flow in them from producers to consumers, how they are transformed, filtered, how streams can be merged. But it all goes more or less in one direction. Actors give you more freedom than that because they can collaborate and communicate just like we humans do. In particular, we will talk about how actors can create other actors, how they change their behavior over runtime, how they exchange messages. And in the end, we will conclude with a lesson about how to test actor systems so that you are well equipped to solve the exercises. Before we dive into what actors are, let us first take a look at why we want to investigate them and where they came from. The actor formalism was first published by Hewitt, Bishop and Steiger in 1973, and what they wanted to achieve is to create a model in which they can formulate the programs for their artificial intelligence research. One of Hewitt's students published his PhD thesis in 1986. Gulager formulated actor languages, so how to write down actor programs, how to reason about them. He described communication patterns between actors and how to use them to solve real problems. In the same year, Ericsson started developing a programming language named Erlang. This is a purely functional programming language whose concurrency model is based on actors and which was then subsequently used in commercial products. In 1995, Ericsson presented their new telecommunications platform, which was highly successful. It quoted a reliability of 9 nines, which means that there was only about 30 milliseconds of downtime per year. This robustness and resilience was made possible by the actor model. Inspired by the success of Ericsson's Erlang, Philipp Haller added actors to the Scala standard library in 2006. Jonas Bonner was then influenced by Erlang as well as the Scala actors to create Akka in 2009. Akka is an actor framework on the JVM with Java and Scala APIs, making the actor model available to a wide range of developers. Actors are applicable in a wide range of problems, and we will see that in the following sessions. But before we go there, let me first show you a few problems which motivate our use of actors. In the past, programs just got faster by using the next generation of CPUs. This was due to an ever-increasing core frequency, but this came to a halt around the year 2005. Since then, CPUs are not getting faster, they are getting wider. This means that instead of making one execution core more powerful, multiple such cores are incorporated within one chip, accessing shared memory. And in some of these, the cores are even virtualized such that one physical execution core can host multiple logical execution threads. There are different ways to benefit from these wider CPUs. The first one is that you can run multiple programs in parallel on the same computer. This is called multitasking and has been done since the first versions of Unix. But if you have a single program which you need to execute faster, then you have no choice but to run parts of the same program in parallel, and this is called multithreading. In order to achieve multithreading, your program must be written in a different way than the traditional sequential form. The difference between running separate programs in parallel and using threads of the same program in parallel is that these threads collaborate on a common task. And if you think about a group of people doing something together, they will need to synchronize their actions, otherwise they step on each other's toes. The same can happen in a multi-threaded program. There are a new class of bugs and problems which await you there, and this is the reason why programs need to be formulated differently in order to be ready for multi-threading. In order to understand what that means, let us take a look at the good old bank account, which was introduced by Martin a few weeks back. This is the class, I just copied it. It contains a field for the balance, and it has two methods: to deposit some amount and to withdraw some amount. Now let us look at the withdraw method in detail. I have marked out here specifically the places where the balance is read and where it is written to. So let us take a look what happens if two threads run this code at the same time. I am making a little table here. Let's say this is thread 1 and this is thread 2. They are executed by different CPUs, so they can run really in parallel. They enter the method with an amount. Let us say that thread 1 wants to withdraw 50 Swiss francs, for example, and thread 2 wants to withdraw 40. The first thing they will both do is read the current balance. In both cases, let us say the balance is right now 80, so they will both see 80. Then both will enter the if statement, the check. Is the amount positive? Yes, it is. And are there actually sufficient funds in the account? Yes, there are. So both will continue. They will calculate the new balance. The new balance in the first thread will be 30, and in the second will be 40. The next thing the threads will do is they will write back the new balance into the balance field of the bank account object. The first thread will write 30, and the second will write 40. This is clearly in conflict, because only one of the writes can win in the end. The one which comes last will overwrite the one which came earlier. This is the first problem which we see here. It is that one of the updates to the balance is actually lost. The other problem is that the invariant of the bank account is violated in that we have withdrawn 50 and 40 Swiss francs, which is 90 in sum, and the balance was only 80. That should not have been possible. One of the threads should have failed, and that did not happen is the other problem with this code. Now what can we do to fix this problem? We need to add synchronization. When multiple threads are working with the same data, they need to synchronize their actions, because otherwise they would be prone to step on each other's toes. What we need to do is to make sure that when one thread is working with the data, the others keep out, like you put a "don't disturb" sign on your hotel door. So let's say in this example we're looking at the balance as the data to be protected, and what we need to do is to put a fence around it, so that when one thread is working with the data, say thread 1, that this one has exclusive access to it, which means that thread 2 here, if it tries to access the data, it will actually be denied access at this time, and it has to wait until thread 1 is finished with it. This way the balance will be protected, and all modifications done on it are done in a consistent fashion, one after the other. We also say serialized. The primary tools for achieving this kind of synchronization are lock or mutex, which is basically the same concept as shown just previously, or a semaphore, where the difference is that multiple but only a defined number of threads can enter this region. In Scala, every object has an associated lock, which you can access by calling the synchronized method on it. And it accepts a code block which will be executed in this protected region. How do we apply this to the bank account to make it synchronized? Well, we have the withdraw method here, and if we put all of it inside of a synchronized block, then reading the balance here, performing the check and writing it back will all be done as one atomic action, which cannot be disturbed by another thread executing withdraw at the same time. That other thread will have to wait. But why do we have synchronized also here on the deposit method? The deposit method also modifies the balance, and if it was not synchronized, then it could modify it without protection, and once the withdraw writes the balance back here, it would overwrite the update performed by deposit at the same time. This is to illustrate that all accesses to balance need to be synchronized and not just the one which we have proven to be problematic. Now let us try to transfer some money from one bank account to another. What we need to do is to synchronize both objects such that they are in a consistent state, because otherwise someone reading the balance of the accounts could find the money in flight. We withdraw from one account, we deposit later into another one. During this time, the money is basically nowhere. And if the invariant which needs to be enforced is that the sum of from and to needs to be the same, this would be violated. Hence, we need to synchronize. So first we take the lock on the from account, then we take the lock on the to account. Now we are safe that no other thread can modify these two accounts, but we can. One property of locks in Scala is that they are reentrant, meaning that the same thread can take it twice or any number of times. It's just a protection against other threads. There is a problem with this code in that it introduces the possibility of a deadlock. Let us say that one thread wants to transfer from account A to account B in one thread, and another thread tries to transfer in the opposite direction. If both start at the same time, they take the first lock, this one on account A, this one on account B. Then they go on to take the other lock. This one will not succeed in taking the lock because it was already taken by the other thread for account B. The same is true for account A in the other thread. This means that none of the threads can make progress. They will both be stuck forever because there is no chance that either of them will yield the lock they already have. This is called a deadlock. There are solutions for this deadlock. For example, to always take the locks in the same order. You need to define an ordering for accounts and so on, and then you could potentially solve this. You will find that there are most of the time solutions of that kind, but they will aggregate and make your code much more complicated over time. And in this case it is simple because both are bank accounts, but what if you want objects to collaborate which do not come from the same code base, for example, and which you cannot modify? In that sense, it would be much better if our objects would not require blocking synchronization, because blocking is what really makes the deadlock happen, because one thread gets blocked on the lock. The other problem with blocking is that it is bad for CPU utilization. If there are other threads to run, then the operating system will run them, but otherwise the CPU will be idle. And waking it up or getting a thread back to run when some other thread has interrupted it takes a lot of time. So your program will run slower if you use blocking. Another problem with blocking objects is that synchronous communication couples sender and receiver quite strongly because the sender needs to wait until the receiver is ready. So if I call a bank account which is synchronized, that bank account will block me until it is ready. Non-blocking objects are exactly what actors are, and we will see that in the next lecture.